Good day everyone, I am Judy Nasipo. Today I will be discussing the topic 5 which is bases and dimension, two of the most important concepts in linear algebra. These concepts help us understand how vector spaces are built and how we measure their size. By the end of this presentation, you will know what basis is, what dimension means, the important rules involving them, and how to solve problems. First, let's define bases. A basis is a set of vectors in a vector space that satisfies two conditions. The first condition is that the vectors must span the vector space. This means that every vector in that space can be expressed as a linear combination of the basis vectors. The second condition is that the vectors must be linearly independent. Being linearly independent means that none of the vectors can be created by combining other vectors. In other words, every vector contributes something unique. A good way to think about a basis is to imagine you're building a house. You only need the essential building materials. If you have extra materials that don't contribute anything new, they're unnecessary. A basis is similar because it contains only the essential vectors needed to generate the entire vector space. That's why a basis is called the minimal set of ingredients. Every vector in space can be written in one and only one way as a combination of these basis vectors. This is represented by the formula V equals C sub 1 V sub 1 plus C sub 2 V sub 2 plus up to C sub n V sub n. Here's the values C sub 1, C sub 2, and so on are called coefficients, and they tell us how much of each basis vector is needed. Now let's move to the concept of dimension. The dimension of a vector space is simply the number of vectors in any basis of the space. One important thing to remember is that no matter which basis you choose, the number of basis vectors is always the same. This is guaranteed by the basis theorem. You can think of dimension as the number of independent directions available inside the space. Let's look at some common example. In R squared, which is the xy plane, the dimension is 2 because two independent vectors are enough to describe every point. In R cubed, ordinary three-dimensional space, the dimension is 3. In R power of n, the dimension is simply n. For the polynomial space P sub n, where the degree is less than or equal to n, the dimension is n plus 1. Finally, the zero space, which contains only the zero vector, has a dimension of 0. So, dimension tells us how many independent vectors are needed to completely describe a space. Now, let's discuss the important rules. The first is the basis theorem. It states that if a vector space has dimension n, then any set of n linearly independent vectors automatically forms a basis. This means we don't have to separately prove that the vectors span the space. The second rule is the spanning shortcut. If we already have exactly n vectors that span an n-dimensional space, they are automatically a basis. Again, there's no need to check linear independence separately. The third rule is the subspace rule. If W is a subspace of V, then the dimension of W can never be greater than the dimension of V. It can only be equal if the two spaces are actually the same. The last rule is the counting rule. A basis of n-dimensional space always has exactly n vectors. If there are more than n vectors, some of them must be dependent. If there are fewer than n vectors, they cannot span the entire space. These shortcuts save a lot of time in solving problems. Now let's apply what we've learned. Example number 1, we are asked to determine whether the set S is equal to the set of containing vectors 1, 2, 3, 0, 1, 4, and 0, 0, 1 is a basis for R cubed. First, we count the vectors. There are 3 vectors, and since R cubed has dimension 3, the number of vectors is correct. Next, we test whether the vectors are linearly independent. We form a matrix using these vectors and compute the determinant. So determinant is 1. Since the determinant is not equal to 0, the vectors are linearly independent. Finally, by the basis theorem, because we have 3 independent vectors in a 3-dimensional space, they automatically form a basis. Therefore, S is a basis for R cubed. Sample number 2. We are given the subspace W is equal to span vectors of 1, 2, 1, 2, 4, 2, 1, 1, 0. And we are asked to find each dimension and the basis. First, observe the vectors carefully. Notice that the second vector, 2, 4, 2, is simply 2 times the first vector. Because of this, the second vector does not contribute a new direction. So, we remove it. Now we check the remaining vectors. The first and third vectors are not scalar multiples of each other, so they are linearly independent. Therefore, these 2 vectors form a basis for W. Since the basis contains 2 vectors, the dimension of W is 2. So the answer is the basis is 1, 2, 1, 1, 1, 0. And dimension W is equal to 2. To conclude, a basis is the smallest set of vectors that is both linearly independent and spans a vector space. The dimension tells us how many vectors are in that basis, giving us a measure of the size of the vector space. The basis theorem, spanning shortcut, subspace rule, and counting rule help us quickly determine whether a set form a basis and what the dimension of a space is. These ideas are fundamental in linear algebra because they allow us to describe, compare, and analyze vector spaces efficiently. And that's all. God bless us all.